Now listen carefully, because this is where most people get it wrong. And I want you to feel it the way it actually is, not the softened version that makes space exploration sound heroic and clean and inevitable. Imagine just for a moment that you've been selected for the most ambitious mission in human history. Not Mars, not some orbital station, but Neptune, the distant blue giant, sitting so far out in the dark that even light, the fastest thing the universe allows, takes more than 4 hours to get there. You train for years, your body reshaped, your mind conditioned, every system rehearsed until it feels automatic. And when the day finally comes, you step into a machine that represents the peak of human engineering, the sum of decades of ambition, calculation, and stubborn refusal to accept limits. And right before you go, there is a truth that no one puts on the poster. No one says out loud in the ceremony. No one frames as the headline of the mission, because it changes everything about how you would see what you're about to do. You are not coming back. Not because something will explode, not because the mission is expected to fail, not because of some dramatic catastrophe waiting out there in the dark, but because the journey itself quietly removes the possibility of return long before anything goes wrong. And this is the part I need you to understand, because it's not emotional, it's not philosophical, it's not negotiable, it's physics. And physics does not care how badly you want something to be possible. You can have the best engineers, the most advanced materials, the strongest motivation humanity has ever produced. And none of that changes the underlying equations that govern motion. Energy and distance, when people hear that a mission is too far, they imagine inconvenience, longer travel time, maybe higher risk, but still within the realm of effort and determination, as if pushing harder solves the problem. That intuition works on Earth. It even works a little within the inner solar system. But beyond a certain point, it breaks completely. And Neptune sits far beyond that point. The scale alone begins to distort everything you think you understand, because you're no longer dealing with a journey measured in months or even a few years, but in spans of time long enough to reshape a human life. And every additional kilometer doesn't just add distance, it compounds energy requirements, communication delays, and the physical strain on the systems keeping you alive. And here's where it becomes unavoidable. To go there, you need fuel, a lot of it, but if you want to come back, you don't just need fuel for the return, you need to carry that fuel with you from the start, which makes the spacecraft heavier, which means you need more fuel to accelerate that extra mass, which then requires even more fuel to carry that fuel, and the logic loops back on itself in a way that doesn't stabilize. It escalates. This is not a design flaw you can optimize away or an engineering challenge waiting for a clever breakthrough. It's built into the mathematics of motion itself. Every attempt to make the mission round trip turns the vehicle into something larger, heavier, and more demanding, until eventually you are no longer talking about a spacecraft, but something so massive it cannot realistically be launched at all. So what do? You remove the return, not as a dramatic sacrifice, not as a heroic gesture, but as a necessity forced on you by the structure of the problem. The mission simplifies the moment you stop asking how to come back, because suddenly the mass drops, the fuel requirements become manageable, and the equations stop spiraling out of control. And that is the quiet pivot where exploration turns into exile, where a journey stops being temporary and becomes, in every meaningful sense, a departure from the world you came from. And that's the part no one tells you before you say yes. You will never come home. Now, before you go any further with me, I need you to stop trusting your intuition, Because the thing about distance in space is that your brain was never built to understand it. And if you rely on that instinct, the quiet feeling that something is far but manageable, you will completely miss what this journey actually means. So let's rebuild that intuition from the ground up. Slowly, carefully, and in a way that forces you to feel the scale instead of just hearing numbers pass by. Start close, because that's the only way this makes sense. The moon sits about 384,000 kilometers away from Earth. And even that, even something we casually look at in the night sky, already stretches human capability to its edge. Light takes just over a second to cross that gap, and the Apollo missions needed 3 days to get there, which already feels like a meaningful journey. Something distant enough to require planning, risk, and commitment, something that sits just outside the comfortable reach of everyday experience. You look at the moon and your mind says, yes, that's far. That's what far feels like. Now take that sense of distance and stretch it. Mars, at its closest approach, sits about 55 million kilometers away, which is roughly 143 times farther than the moon. And suddenly the numbers stop behaving intuitively, because you can no longer picture stacking that distance in your head. Spacecraft takes 6 to 9 months to reach it. And even then, that's during the brief windows when Earth and Mars align favorably, which means that even in our own inner solar system, distance already dictates opportunity, timing, and the structure of missions in ways that feel almost restrictive, and yet, even here, you can still imagine it. Still compress it into something your brain can loosely hold. Now let go of all of that, because Neptune is not just another step outward. It is a different regime entirely. On average, Neptune is about 4 billion kilometers from Earth, not million billion, and that single change in scale is where your intuition quietly fails you. This is not Mars multiplied. It is not a longer version of a familiar journey. It is something that exists outside the range your mind evolved to process. Light itself, the fastest thing in the universe, takes over 4 hours to travel that distance, which means that everything you think of as immediate communication simply ceases to exist. If something goes wrong out there, if you send a signal back to Earth, you will wait 4 hours before anyone even knows you are in trouble, and another 4 before a response can return. That is not delay. That is isolation built into the fabric of space. And here is the part that really shifts your perspective. If you let it, the only spacecraft humanity has ever sent to Neptune, Voyager 2, took 12 years to arrive, moving along a carefully calculated path that used the gravity of multiple planets to accelerate itself in a rare alignment that won't happen again for another century. 12 years. And that was a lightweight probe, carrying no life support, no crew, no requirement to sustain anything fragile or alive. Just instruments, electronics, and a mission designed from the beginning to never come back. When you place yourself into that timeline, when you imagine not a probe but a human life stretched across that same span, the distance stops being abstract and starts becoming something that presses on time itself, reshaping what a journey even is. Because distance at this scale is not just about how far you travel, it is about how long you exist within that travel. How many years pass while you were suspended between where you came from and where you were going? How the idea of arrival slowly detaches from anything familiar. The further you go, the less Earth remains part of your present, until it becomes something you remember rather than something you are connected to. And that transition doesn't happen all at once. It happens gradually, almost invisibly. As communication stretches, as delay becomes normal, as the rhythm of life on Earth slips out of sync with your own. The moon was never far, Mars was never far. You just never knew what far really meant. Now you might be thinking, all right, distance is enormous. Communication is delayed. The journey stretches across years. But none of that sounds fundamentally impossible. Just difficult. Just a matter of building something powerful enough, fast enough, efficient enough to bridge the gap. That instinct is natural, and it works almost everywhere else in life. Because when something is hard, we assume we can scale up effort, add more energy, push harder until the problem yields. But propulsion doesn't behave like that. And this is where I need you to follow closely. Because the rules change in a way that feels almost unfair. Every spacecraft you've ever heard of, every mission from Earth to the Moon, to Mars, to the outer planets, is governed by a relationship that seems simple at first and then turns quietly oppressive the longer you stare at it. To go faster, you need to carry fuel. To carry fuel, you need structure, tanks, engines, mass, and to accelerate that mass, you need even more fuel. It sounds manageable until you realize that fuel itself has weight, and that weight demands still more fuel to move it. And suddenly you are caught in a loop that doesn't stabilize. It escalates. This is the rocket equation. And engineers don't call it difficult or inconvenient. They call it tyrannical, because once you step into it, it dictates terms. You cannot negotiate with, let's make this real for you. Imagine you want to reach Neptune in less than a decade, which already feels like a compromise, already stretches human endurance. You build a spacecraft with enough fuel to accelerate toward that distant orbit, enough life support to keep a crew alive for years, enough shielding to survive radiation, enough redundancy to handle failures no one can predict in advance. It's already massive. Now add one more requirement. You want to slow down when you get there, because flying past Neptune at high speed isn't enough. You want to enter orbit to stay, to study. That means you need fuel reserved for deceleration. But that fuel has been sitting with you the entire journey, adding weight from the moment you launched, which means the initial burn, the one that gets you off Earth and onto that trajectory, now needs to be stronger, which means you need more fuel at launch. And that additional fuel adds more mass, which again requires more fuel to move it. The loop tightens, each step feeding the next, and the numbers start growing not linearly, but exponentially, until the vehicle you are designing no longer resembles a spacecraft in any practical sense. It becomes an accumulation of propellant carrying, with the crew and their fragile systems buried somewhere inside like an afterthought. Now take it one step further, because you're not done. You want to come back. So you need fuel, not just to slow down at Neptune, but to leave Neptune, accelerate back toward Earth, and then slow down again upon arrival. That means carrying return fuel across the entire outbound journey, which means increasing mass again, which means increasing launch requirements again, which means increasing fuel again. At some point, the math stops bending. It doesn't matter how clever your design is, how efficient your engines are, how determined your mission planners might be. The structure collapses under its own requirements. There is no clever trick hiding in the margins that rescues you from this. People sometimes suggest advanced propulsion, nuclear thermal rockets, ion drives, fusion concepts, all of which offer improvements, some dramatic, some incremental. But none of them break the underlying relationship between mass, energy, and velocity. They shift the curve, but they do not erase it. You are still paying for every kilogram you carry And when you try to carry everything needed for a round-trip human mission to Neptune, the cost spirals beyond what current technology can even approach. So the question changes, not because you want it to, but because the equation forces it to. You stop asking how to make the mission faster, or safer, or more efficient, and you start asking what you are willing to remove. And the most expensive thing you can remove, the one that simplifies everything else, is the return. The moment you do that, the mass drops, the fuel requirements fall back into something that at least resembles possibility, and the system stops collapsing under its own weight. Every solution creates a bigger problem, and eventually the math stops giving you options. Now let's talk about where you're actually going, because up to this point the journey itself has already started to fall apart under distance and propulsion alone. But even if you could solve those problems, even if you could build something powerful enough to cross that enormous gap, you still have to face the destination, and Neptune is not just another planet waiting quietly at the end of a long trajectory. It is a place that resists the very idea of human presence at almost every level you can think of. When you picture a world, your mind instinctively looks for a surface, something solid, something you can stand on, a horizon you can orient yourself against. But Neptune doesn't offer you that. It is an ice giant, which sounds almost approachable until you realize the name is misleading, because there is no frozen landscape waiting for footprints, no stable ground beneath your boots, just an atmosphere that deepens and thickens as you descend, layers of hydrogen, helium, and methane swirling into something that becomes harder to define the further you go. The blue color, that deep cobalt you've seen in images, comes from methane absorbing red light, leaving behind that cold, almost serene appearance. But that calm color hides a system that is anything but gentle. The winds alone should stop you, speeds exceeding 2,000 kilometers per hour tear through the atmosphere, faster than anything we experience on Earth, faster than the strongest hurricanes ever recorded. And these are not isolated events, not temporary disturbances, but part of the ongoing dynamics of a planet driven by internal heat and complex fluid motion that we still don't fully understand. Voyager 2 captured the great dark spot, a storm system roughly the size of Earth. And unlike the long-lived storms on Jupiter, Neptune seemed to appear and disappear over years, forming and dissolving in ways that remind you how incomplete our understanding still is. You are not arriving at a predictable system. You are arriving at something that shifts on timescales that outpace your ability to fully map or anticipate it. And then there is the magnetic field, because even the invisible structure of the planet refuses to align with expectations. On Earth, the magnetic field is roughly aligned with the rotational axis, giving us stability, predictability, a sense of orientation. Neptune's field is tilted by about 47 degrees and offset from the planet's center, which means it behaves in ways that complicate navigation, radiation exposure, and any attempt to model the environment in a straightforward way. It suggests that the field is generated not in a central core, but somewhere in the outer layers, in a region we barely understand, adding another layer of uncertainty to a place already defined by extremes. And just when you think the planet itself is enough, you look outward and find Triton, its largest moon, orbiting in the opposite direction of Neptune's rotation, a captured object from the outer solar system, a world that never belonged here in the first place. Its surface temperature sits around minus 235 degrees Celsius, making it one of the coldest known objects in the solar system. And yet it is active, violently, so in its own quiet way, with geysers of nitrogen erupting through its frozen crust, sending dark plumes kilometers into a thin, fragile atmosphere. This is not a dead world. It is a strange, dynamic system operating at the edge of what we understand as geological activity. Even the rest of the system reflects that instability, with moons following eccentric paths, with orbits that hint at a history of capture, collision, and rearrangement, and over long enough time scales, even Triton itself is doomed, slowly spiraling inward until tidal forces tear it apart, forming a ring system that will briefly outshine Saturn's before dispersing again. Nothing here is stable in the way you expect. Nothing is preserved. Everything is in motion toward some transformation you will never witness. This is the destination you have spent years trying to reach, a place without ground, without stillness, without any natural accommodation for something like you, a system that does not resist you violently in a single moment, but instead offers no foothold at all, no place to exist except within the fragile shell of the machine that brought you there. Neptune isn't waiting for you. It never was. Let me pull you closer to this part, because everything we've talked about so far, distance, fuel, propulsion, those are still problems you can imagine solving with better machines, stronger materials, more advanced physics. But this is different, because here the limiting factor isn't the spacecraft, it's you. And the uncomfortable truth is that your body is not built for the environment you're about to spend years inside. On Earth, you live inside layers of protection, so effective they become invisible to you. The atmosphere absorbs most of the high-energy radiation coming from space, and the magnetic field deflects charged particles that would otherwise pass straight through your body, damaging cells at a microscopic level. Step beyond that protection, move out past Earth's magnetosphere, and you are no longer shielded. You are immersed in a constant stream of cosmic radiation, high-energy particles that penetrate tissue, break DNA strands, and leave behind damage that your cells can only partially repair. This isn't a sudden injury, not something you feel in a moment, but a slow accumulation, a quiet degradation that builds year after year. A journey to Neptune, whether it takes 5 years or 12, would expose you to radiation doses far beyond what current safety limits consider acceptable, and every additional month adds more damage, more mutation, more strain on systems that were never meant to handle this level of exposure for this long, and there is no simple solution waiting to fix it. You might think of shielding, thicker walls, denser materials, but high-energy radiation behaves in ways that complicate that idea. When these particles strike heavy shielding, they can create secondary radiation, fragments that scatter and sometimes make the internal environment even more hazardous. Water can help absorb some of it, but water is mass. And mass is the very thing your spacecraft cannot afford to carry in excess. So you are left managing a problem you cannot eliminate, only endure. Then there is gravity, or more precisely, the absence of it. Your body is built around the constant pull of Earth. Every system tuned to that force in ways you rarely consider. Bones maintain their density because they are under continuous stress, supporting your weight, resisting gravity with every step you take. Remove that stress, and the body adapts by shedding what it no longer needs. In microgravity, bone density decreases month after month. Calcium leaching away into the bloodstream, the structure becoming weaker, more porous, more fragile, over a journey measured in years. This isn't a minor loss. It's a transformation. The skeleton that arrives at Neptune would not resemble the one that left Earth in any meaningful functional sense. Muscles follow the same path. Without gravity, they are no longer required to support your body. And like any unused system, they atrophy, even with rigorous daily exercise. Astronauts on the International Space Station lose strength and mass over months. Extend that to years, to a decade or more, and the decline becomes something you cannot fully counteract. The body reaches a new equilibrium, one that is optimized for weightlessness but catastrophically unprepared for gravity. The heart, too, adapts in ways that sound subtle until you realize what they imply. On Earth, it constantly works against gravity to pump blood upward, maintaining circulation throughout the body. In microgravity, that resistance disappears, and the heart no longer needs to exert the same effort. Over time, it weakens, losing mass, becoming less capable of handling the demands it once met effortlessly. Blood volume decreases. The entire cardiovascular system recalibrates to a world where up and down no longer exist. And when that system is suddenly asked to function again under gravity, it struggles, sometimes to the point of failure. Even your senses begin to shift. Fluids in the body redistribute without gravity. Increasing pressure in the head, affecting the eyes and the optic nerve. Some astronauts return from relatively short missions with lasting vision changes. Stretch that exposure across years, and you are no longer talking about temporary adaptation, but permanent alteration. The way you see the world may not survive the journey intact. All of this happens before you do anything at Neptune, before a single experiment, before a single orbit, before any of the scientific goals that justified the mission in the first place. The journey itself becomes the defining event, a prolonged process of biological erosion that reshapes you at every level, quietly, continuously, without any dramatic moment you can point to and say, this is where it began. By the time you arrive, your body no longer belongs to Earth. There is one more layer to this that doesn't show up in equations, doesn't appear in engineering diagrams, and can't be solved by adding more fuel or stronger materials, and yet it may be the one that determines whether the mission holds together or quietly unravels over time. It's not distance, not radiation, not even the physical decay of the body. It's what happens to a human mind when it is cut off from the rest of its species for years, then decades, with no way to close that gap. At first, it doesn't seem so severe. You still have communication. After all, you can send messages back to Earth, receive updates, hear voices, see recorded faces, but the delay changes everything in ways that are subtle at first and then impossible to ignore. At Neptune's distance, every signal takes about 4 hours to reach Earth, and another 4 hours for a reply to come back. That means every conversation stretches across 8 hours at minimum. You ask a question, and by the time you receive an answer, the emotional moment that created the question has already passed. There is no interruption, no shared laughter, no immediate reaction. The rhythm of human interaction, the back and forth that defines connection, simply disappears. And what replaces it is not silence, but something stranger, a delayed echo of humanity, always out of sync with your present. News arrives hours late, a discovery, a celebration, a tragedy. You learn about it long after it is unfolded. And by the time your response returns, Earth has already moved on. Over time, this doesn't just feel inconvenient. It begins to feel unreal. as if you are no longer participating in the same timeline as everyone else. You are still human, still connected in a technical sense, but not in the way that matters for daily life, for emotion, for shared experience. Inside the spacecraft, the crew becomes everything. Every interaction, every conversation, every conflict, every moment of support comes from the same small group of people day after day, year after year. There is no leaving the room, no stepping outside, no meeting someone new, no resetting the social environment. The group must sustain itself entirely, resolving every disagreement internally, absorbing every tension without relief, maintaining cohesion not for months, but for decades. Even in carefully controlled simulations on Earth, Mars habitat experiments, Antarctic stations, submarine deployment, psychological strain appears after just months. Small irritations grow, conflicts intensify, motivation fluctuates. Now extend that to years, then to 25 years, and the scale of the challenge becomes something we have never truly tested. And then there is time itself, not as a measurement, but as a lived experience. While you are traveling, Earth continues. People age, relationships shift, families change, someone you love may die, and you will learn about it hours after it happens, respond hours later, and never stand in the same room again. Entire phases of life pass without you. Cultural changes, technological shifts, events that reshape the world. You witness them as a delayed observer, never fully present, never fully involved. The place you left behind slowly becomes something unfamiliar, not because it has disappeared, but because you have been absent from its unfolding. Even if the crew remains stable, even if no one breaks under the strain, there is a deeper transformation taking place. The group becomes its own reference frame, its own small version of humanity, operating under different constraints, different rhythms, different priorities. Decisions that would once be external become internal. Identity begins to shift, not dramatically, not in a single moment, but gradually as the connection to the larger human context weakens. You are still human, but the meaning of that begins to drift. There is no emergency exit from this condition, no quick return, no intervention team, no way to restore the immediacy of connection that defines life on Earth. Everything that happens, every emotion, every fracture, every reconciliation stays within that closed system, carried forward day after day, year after year, with no outside reset. At that distance, you are no longer part of humanity in real time. If you step back and look at everything we've walked through together, it becomes clear that there isn't a single point where the mission fails. No dramatic barrier where progress suddenly stops. No one equation or limitation. That alone makes a human journey to Neptune impossible. What you find instead is something more decisive, a chain of constraints that reinforce each other, each one severe on its own, but together forming a structure that current human capability cannot push through without breaking somewhere along the way. The distance stretches travel time into years and then decades, which immediately turns exposure into a central problem rather than a secondary one. Radiation is no longer a manageable risk, but an accumulating certainty, steadily degrading the body at a level that cannot be fully shielded against. Weightlessness ceases to be a temporary inconvenience and becomes a condition that reshapes bone, muscle, and the cardiovascular system into forms that are incompatible with the environment. The crew would eventually need to return to. The propulsion problem ensures that every attempt to design a round-trip mission feeds back into itself. Increasing mass increasing fuel requirements until the vehicle required to make the journey no longer fits within the limits of what can be launched or sustained. And layered over all of this is the psychological reality of isolation of a crew existing out of sync with the rest of humanity for a span of time long enough to alter identity itself. None of these factors can be ignored, and more importantly, none of them can be solved in isolation. You cannot fix radiation without adding shielding, which adds mass, which worsens propulsion. You cannot shorten travel time without more powerful engines, which again increases mass, complexity, and energy demands. You cannot preserve the human body without artificial gravity or new biological interventions, both of which introduce further engineering challenges that feed back into the same constraints you were trying to escape. Every attempt to relieve one pressure intensifies another. The system doesn't fail because we haven't tried hard enough. It resists because the underlying relationships between energy, mass, time, and biology are all pointing in the same direction. And yet, Neptune is not beyond our reach. Not in the broader sense. We have already touched it, if only briefly, through Voyager 2, a machine that crossed billions of kilometers without needing air, without needing gravity, without needing to come home. It sent back images of a world we had never seen before, data that reshaped our understanding of the outer solar system, all while operating within constraints that would be lethal to a human crew. Future missions will go further. More advanced probes, orbitas, perhaps landers for Triton, equipped with better instruments, better propulsion, designed to survive where humans cannot. They will map the atmosphere, measure the magnetic field, analyze the chemistry, and return knowledge that expands our understanding without risking lives that our current technology cannot adequately protect. This is not a failure of ambition. It is a recognition of scale. The universe does not adjust itself to match the timelines, lifespans, or biological limits of the beings trying to explore it. It operates according to its own rules, consistent, indifferent, and vast beyond what our instincts are prepared to grasp. We move forward by understanding those rules, not by ignoring them, and sometimes that means accepting that the form of exploration we imagine human footsteps. Human presence must wait until our tools, our physics, or even our biology evolves to meet the challenge. The stars are still there. Neptune is still there. The path to reach it with machines is already open, and the path to reach it with humans may exist someday, but not yet. Not under the constraints we currently live within. Not without solving problems that sit deeper than engineering and closer to the foundations of how matter and life behave in the universe. The universe doesn't stop you. It simply continues without adjusting for you.